So first we should do is like as what we did yesterday. We have some warm up problems, and to kind of to warm up our brains for a little bit. So to, this problem, I saw this problem on Terence Tao's blog. So Terence Tao is a full professor in mathematical department at UCLA, and he is a Australia American mathematician, and he is very famous because his IQ is quite high, and he is the only two people have the record that when he was 8, he got his SAT score is more than got SAT score is higher than 700. Okay, so yeah, I saw this problem on his blog, so I want to share with you guys so we can warm up our brain a little bit. So that's first some setting up. So here is the problem. The puzzle is called the Blue-Eyed Islander puzzle. So basically, some settings. So there is a island, and there are. So I changed the number a little bit. It's not exactly the same as what I saw on the blogs to make it simple. So then I saw on an island there are 100 people, and 100 people, and we know there are 95 of them. They have red eyes, and 5 of them have blue eyes. And we know that this is the setting. And there are some rules on this island. So the first rule is it is forbidden for them to know their own eye color or even discuss the topic. So although we know there are 95 red eyes and 5 people blue eyes, they don't know this. They only know, the only thing they know that they can saw, each resident can saw other people's eye colors, but they don't know their own. Okay, they can see, for example, there's one people they can, if the you can see all the rest of the 99 people what their eye color is. Okay, there's an even strange rules is that if a person discover his or her own eye color, what he will do, he or she will kill himself, will commit suicide at the noon the following day in front of everyone, basically in the village square for all to witness. So yeah, if they know somehow figure out their eye color, they will kill themselves the next day at noontime. Okay, so those people, this 100 people live on the island for quite a long time. Nothing happened. So until one day, okay, a blue-eyed foreigner visits the island, and they have a great time. And before this guy left, he made the following statement to everyone. So I'm glad to see that, to see other blue-eyed person like myself on the island. Okay. So after he said that, he kind of say, yeah, he knows the rules. Somehow it feels like, yeah, we should not discuss about this. So she kind of feel, yeah, we should not, it's not appropriate to do that. And but he also think maybe, yeah, they can see each other's eyes. They all know they are blue eyes, they're also red eyes. It didn't seem I bring any new information. So here is the question. So what is the effect of this statement? The foreigner thinks it is okay. I didn't bring any new information, but there is another argument. The first argument is that the foreigners think. So because all those residents, all those people can see other people's eyes. They know they are blue eyes on this island. They didn't bring any information. So nothing will happen. This is argument one. The second argument is, so 5 days later, so all those blue-eyed people will commit suicide together. So yeah, I give you guys 20 seconds. You guys can think. If you want to share your what you're thinking, you can in the chat to show which argument you support. So I'll give you 20 seconds. So anyone want to share which argument they want to support? Okay. Actually, it seems to, yeah, actually it's the second one. So 5 days later, all those blue-eyed people will commit suicide. Okay, let me see on the chat. Since they all, yes, yes, some people choose the second one. Yeah, great. So actually, the interesting thing is why is the second one is the right answer? Why after 5 days they all kill themselves? The truth is the second argument seems, yeah, it's kind of, yeah, because yeah, otherwise this second argument is too specific. So so then it's some, yeah, they must know something that can make this argument. So the most interesting is why this is true. So basically, I will try to explain a little bit. So first, assume there is just there's 100 people. There's only one people in this 100 people. There are only one people with blue eyes. The rest of 99 people, they have red eyes. Okay. Then after the foreigner said, okay, I'm glad there's another guy with blue eyes. Okay, because this guy can see knows the rest of the people's eye color. Okay, then they know they're all red. And he also know that there is one person, at least one person, have blue eyes. So that's the only thing could happen is itself. So if only one people with blue eyes, this guy will commit suicide the other day, the next day at the noon time, because he know all the rest, all the 99% have white eyes. Only he don't know his own eyes, but that foreigner tell that there's at least one blue eyes, and that must be him. So he figure out his eye color, he will kill himself. Okay, so then what about if 2 people with blue eyes and the 98 people with red eyes? So if this situation happen, what will happen? Okay, and think about you, if you are the guy with the blue eye, and that guy said, the foreigner said there's another guy with blue eyes, So he look around, he saw that, yeah, at least there's the one guy with blue eyes, and he know if he is the only one with blue eyes, he will kill himself the next day. And then he wait till the next day. He saw, yeah, that guy with blue eyes will kill himself. And he wait the next day and no time to see, yeah, to see what happened, but nothing happened. Then he'll think, why nothing happened? If that guy is the only one with blue eyes, he will kill himself. Okay, then the only thing could happen is that guy also see another person with blue eyes. So that's because he know all the rest are red eyes and one is another blue eyes, that the other person with blue eyes could only be himself. Okay, then actually both the people with blue eyes have, if using the same logic, they will figure out they have the blue eyes. So that's why on the second day, this is on the first day. First day, they kill the 2 people. The second day, kill himself. And think about 3 people, same thing. So if the guy with blue eyes, he saw other 2 people with blue eyes. If that's the only 2 people with blue eyes, they will kill themselves on the second day, but they don't. So he figured out his eyes is also blue. So basically on the third day, he will all 3 of them figure out that they have blue eyes, they will kill themselves. Okay, so basically that's why after 5 days, because we have, for this problem, we have 5 people with blue eyes, 95 with red eyes. That's why after 5 days, they all the blue eyed people will kill themselves. Okay, this just of a puzzle for fun. Let me see the comments. So, okay. So the only suicide will happen if they know their own eyes. They don't know their own eyes. They can see the rest. They can see the 99 rest of people, their eye color, and they don't know this information. The information is for us. Another information, they don't know there are 95 and 5. They don't know this. They only know the 1995. For example, you have the blue eye, you only know there are 95 with red eyes and the 4 people with blue eyes. So that's, if you have the red eye, so you know the 5 people with blue eyes and the 94 people with red eyes. And they don't allow them to discuss this. So they don't know. Actually, there are 5 people with blue eyes, actually. Only the red eye people know that. The blue eye people didn't know that how many blue eyes in there because they don't know their eye color. Otherwise, they will kill themselves. Okay, so let's so they need the statement by who to see. Okay. Okay, so if you have questions about this, you can, yeah, maybe you can speak. I think it's very hard for me to read those comments. If you want to make comments, you can, yeah, speak up so we can discuss. So if not, then we can, yeah, go to the real meet. Okay, okay, so if nobody want to discuss this, then we continue to talk about for loops. Okay, yesterday, so first some recap. Yesterday we talking about the for loop. Basically, the what for loop is used for is actually to make our code to be compact. So basically, this is, yeah, if you, yeah, originally we should write the code like this, but we finding out most of them, yeah, they actually the identical code. Only one thing is changing. So in order to make the code compact, so then we invent this for loop, and the syntax of the for loop is, so basically we start with for, then showing this is a variable that is changing, is iterative, it's keep changing, and changing based on this range. This range is 0, 1, 2, till 8. So this I will be equal to 0, 1, 2, and 8. And when each time he is assigned a number here, he will implement this block of codes. So then, so for example, I equal to 0 and implement this, and I equal to 1 and implement this again, and I equal to 2 until I equal to 8. He implement this the last time. Then after that, the for loop is finished. We can go to execute the second line, execute this line of code. Okay, this is basically the syntax, and we are talking about how to using for loops to finding a number, any number, to check, to do prime test to check whether any number is a prime number or not. So here, so let's go back to how to show how we can actually using for loop to help us identify, to check whether a prime, whether a number is a prime number or not. Okay, so first we utilize the definition of the prime number. So let's review what is that. So a prime number is must be a positive and the integer, and it should be larger than 1, and only have no other factor except 1 and itself. So here is some example 2. It's first, it's an integer, it's a positive 1, it's larger than 1, okay? And for 2, only have 2 factors, 1 and 2. So basically, based on the definition, we know 2 is a prime, and 3, same thing. 1 and 3 is only 2 factors, so 3 is a prime. So based on the same argument, 5 and 7, they're all prime. Okay, but 6 is not, because 6, 1, 2, 3, and 6, they're all factors of this number, and the prime should have only 2 factors. They have more than 2 factors, basically means 6 is not a prime. Okay, Then yeah, we want to check a given any number. So how to find it? It's whether it's a prime or not. So as I said, basically we need to think, if we want to program this, we need to think about a method or an algorithm to do that. So this one Python cannot help us. We have to figure that out. If we can figure that out, then we can translate our idea into Python code. Okay. So Python just a way to represent your idea that a computer can understand. Okay, so then we need to come up with the idea, how, given a number n, how can we check whether this n is a prime number or not? So we can base on definition. So basically only have, if we have n, so should only have two factors is 1 and n. So basically means all the things 2, 3, 4, n minus 1, all those things here cannot be the factor of this number. So if we check each of them, then they are, and we know they are all not the factors, then we're done. Okay. So basically then, as you see, we keep checking those things. Then this is good for using for loops. Okay, let's show, yeah, the first algorithm is that, yes, we check 2, 3, 4, 5, 6 till n minus 1. And if they are all not factor of n, then n is a prime number. If one of them inside here is a factor of n, then basically n is not a prime number. Okay, then let's go to, yeah, this is good, but as you see, when n is very large, it could be larger than 1 million, even 10 billions, even larger than that. Okay. The prime number. Think about that. How many times we should check this? So basically it means we need to check a lot. If this n is a billion, so basically we need to check a billion times. So which is very, so basically it's very not efficient. So people think, yeah, can we make it faster? So basically they come up the second idea. So here I just briefly show that why they come up this idea. Think about assuming, we don't want to go to a very detail, but just trying to intuitively show that why we can use the second one. Think about this n number, okay, can be represented by a times a, okay, the a is the same. So basically we only need to check whether this a is a prime number, okay? And if it is, we only check from 2, 3 to a. If they are all not factors, then basically we are done. So if any of them is a factor, so basically this is part will be the factor of this part. So basically means we don't need to check all the things till n minus 1. We only need to check till n square root. So this is the basic idea. So basically, yeah, if they can be read like this, we only need to check this part, because this part is exactly the same. We don't need to check it again. So this is the idea. But as you see here we reduce the number of things we need to check. Here we need to almost check n times. Here we only need to check around approximately square root of n times. It's quite already reduce some iteration to checking those things. And then people think, yeah, can we make it even faster? This is actually what computer scientists do. So this is one direction. People always want to invent or develop an efficient or even efficient algorithm, because they want to, for the same task, less time basically means better. So because time is money, yeah, we always want to compute things efficiently. And this is also one of my research interests, trying to solving a problem that to make it fast to get the solution. Okay, so then here is the third algorithm, and basically in this algorithm it utilizes an idea. So basically 6k plus I. So I could be equal to -1, 0, 1, 2, 3, 4. Basically, this equation can represent all the integer numbers. So why? So let me show you the example. So all integer numbers larger than 4. So basically, if you let k equal to 1 and I equal to 0, so this number will be, we should start from -1, right? So this one, -1, and this number will be 5. And the same thing, k equals to 1, I equal to 0, and this will be 6. And the similar thing, I equal to 1, I equal to 2, 3, and 4. We got 7, 8, 9, and 10. And if k equals to 2, I equal to -1, this will be 11. So basically, as you see here, when k increase and we changing k and I, so this equation can be represent any integer number. So if for k larger than 0, larger than this number will represent all the integer number larger than 5, larger than 4. Okay, so then basically, based on this, yeah, people think, yeah, and we can already finding some patterns here. So as you see, let me try to remove this. Okay, let me try to remove this. So basically, we know 6k plus I could represent any number larger than 4 for k, any k larger than 0. Okay, then basically we have 6k minus 1, 6k, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4. Okay, and we're already finding some of the number is not a prime number. This is not a prime number. Why? Because 2 is a factor of this. And this is not a prime number. Why? Because 2 is a factor of this. And this is a prime number. It's not a prime number because 2 is one of the factor. And this is not a prime number because 3 is a factor. So basically, we show that this equation can represent all numbers, all integer numbers larger than 4. And we know 4 of them, they are not prime number. The only thing could be prime number is this 2. So basically, we don't need to check this. We don't need to check this. We don't need to check this. We only need to check whether these 2, when k equal to 1, equal to 2, equal to 3, and compute these 2 numbers to check whether they are the factor. They are a factor of it. Because we know this, definitely this won't be the factor because they already have 2 as a factor of this. So basically, that's why we only need to check this 2. And as we also know, we only need to check up to n square root. So that's why we further reduce the computation time. We don't need to check every number here. Basically, we don't need to check this because we know it's a factor. If we can, is this a factor? Then 2 will be it's the factor of it. So we don't need to check this. We don't need to check this. We need to check 7. So basically, that's why we come up this algorithm 3. Okay. So any questions so far? So basically, after that, I will basically implement all the 3 ideas by using Python code. Here, any questions related to the 3 algorithms? Okay, if not, it's good. Then basically, so one observation we can have is that the number of things we need to check become smaller. Here we need to check n minus almost around n times. Here is only around n times, n square root times. But here we only around actually 3 times. Okay, so basically, as you see, because we don't have so many numbers to check, so it will reduce the time. Okay, let's go and trying to program this. So first, the first algorithm is a very natural algorithm based on the definition. we need to check all those numbers whether to see whether it is a factor. So here's a piece of code. I didn't write it into a function, but it's fine. So basically, so this here is the definition. This is the number we want to check whether it is a prime or not. Here is basically what Ola trying to prove. With Ola already proved this is not a prime number, but we can check that. So first we have a flag. This flag is false, basically means it's a prime number. If this flag is true, it's not a prime number. So basically, as you see, we will change the flag, using this flag as the indicator of whether this number is a prime or not. So then basically, based on the definition, prime number should be greater than 1. Okay, so if this number, for example, is like a -1, then we go here, then we go this if. So if basically, if statement is that if this is true, it will implement the code here. If this is not true, it will skip this part and directly implement the following codes. So think about if n is -1, we first do the check. Is this number NUM? Is this number if NUM is equal to -1? Is this a number larger than 1? Basically, no. So basically, it won't implement everything here. It will directly go here and it will check the flag. The flag here is false. So basically, this if the flag is true, it will do this. If the flag is false, it will do this. Basically, if you see if NUM number is -1, the flag will be false. So basically, we'll go implement this one. We'll show that it's false. False should be here. Okay, I think I made a typo here. So I think if it's true, it's a prime number. It's false, it should be not a prime number. Okay, here I think I made a mistake here. So basically, true means okay. False means it's not a prime number. So basically, as you see, -1 is not satisfied here. It should be not a prime number. Okay, and we should make this true. Initial this as true. Then it's not. It will go here. It's not a prime number. Otherwise, I think I messed up the thing. Okay, we can figure that out. It's okay. So basically, yeah, if this not, then basically it should be not a prime number because it should the prime number should be larger than 1. So this is the flag is false, and yeah, it should be if it's we should have an else here to make this flag. Yeah, if it's not, it should be, yeah, then this should be true. Yeah, we should add this line here. So if it's smaller than 1, basically we should make the flag true, and basically it will show that it's not prime number. Okay. So that's typical. Yeah, when you're coding, even the most experienced programmer will make mistakes. So that's one thing I think you should know about programming. Okay, and although I may not claim I'm a great programmer, so at least for this one. Okay, so this is if this is not true. So basically the major thing we checking here is inside this part. So if you think about here, we have a number which is larger than 1. And basically we need to implement the codes inside here. So here, so basically we're using for loop. Okay. So here we need to make a number that go iterated over to n-1 and check each one whether each of them is a factor. So this is basically what we did here. We make a variable, and this variable is the only thing changing in this for loop. And it will change from, so if you remember what it is range for, from 2 to n number -1. So basically, what do we do? So basically it's like this, I first equal to 2, and then it will implement this block of code. Okay, I equal to 2, then we do checking if it's going to check whether we check whether this number. So I will introduce what is this. This is called the modular symbol in Python. It's called modular operator. It returns the remainder of the dividing the left-hand operator by the. So basically, yeah, let me show you one example. 7, 2 basically equal to 1 because 7 is 2 by 3 plus 1. So we first do the divide. This is a remainder. And if 8, 3, basically this equals to 2 because it's not cannot be fully just divide. Yeah, we know 8 equal to plus 2. This is just the remainder part. So basically, if the remainder like 6, if the remainder is 0, basically means it can, this is a factor. So basically we're using this to check whether I is a factor of this number. If it is, this should be equal to 0. Okay, basically this is what we did here. We're checking whether I equal to 2, basically means we're checking 2, whether 2 is a factor of this number. If it's 0, basically means 2 is a factor. If it's not, yeah, we're done here. If this is true, we go here. If this is not, we check again. We write I equal to 2, equal to 3, because we need to go to n-1. We do this checking to see whether it's equal to 0. If it's equal to 0, basically means it's not a prime number. We set the flag and break up the loop. So break is means although we have lots of number we didn't check, but we're already finding one factor is already tell us that this is not a prime number. So we don't need to checking the rest of the numbers because we already know one factor. So it's already done. The job is already done. Okay. So then, yeah, basically it will do things here. I will equals to all the things here. And what we check is whether it's checking whether this is it is a factor. Oh, yeah, to check whether this is a factor. So if it is not, we don't need to. Yeah, if maybe at some point we're finding out this actually is true, this operation give us exactly 0, basically means it's not a prime number. Then we in this if loop, then we know this is true. Then we just break up. Break means break up the for loop. We don't need to iterate all the following. We don't need to do that because we already know it is a prime number. And we set the flag to be true. And we know true means it's not a prime number. If false means it is a prime number. So this is basically for the first algorithm. So I will go actually show the Python code and actually run it to you guys. Let me share the screen with this one. Okay. Okay. So basically, as you see, here is the Python code for algorithm 1. So basically, as I said, we should. Yeah. So basically, then we can check if this number is smaller than 1. It will show that it's not a prime number. Okay. Basically, okay. Yeah, but yeah, then we're going to check. Yeah, this number is what all are trying to prove that it's not a prime number. So this basically what we have. We're basically finding out this is not a prime number, and we're also finding out this number basically equals to this number times this number. Basically means these two are both factors of this number. So this is not a prime number. And here we also want to show the time. So how many times we need to execute the execution time for those part of codes. So basically what we do here, we need to use another modules in Python is time. Basically here, we just record the clock time on the computer in here. And then, so then we run all those code. And at the end, after we finish all those code, we get the clock time, computer clock time again, and the minus the one we already have at the very beginning. And the difference is the time that spent by the piece of code. Okay, here, yeah, this one we know, although it looks quite large, but we're finding out, we only did like 600, around 600 check, just finding one factors. So it doesn't take a long time. It's like quite small number of time. Here I give two other numbers, and I know those two numbers are prime numbers, and I just want you guys to see that the time it will use. Basically, this number to see how large it was 16 million. So basically, it's a prime number. Basically, we need to check 6 million times to see how long it takes. Yeah, as you see, it takes a longer time, 1.5 seconds. Okay, and here is an even larger number, and we know it is a prime number. Let me run this. Yeah, this one is also prime number to see what is this is. I think it's, yeah, a billion, more than a billion. It's quite a large prime number. And let's see how long it takes. So if you see this, basically means it's, yeah, if you see this, basically means it's just keep running. Yeah, as you see, we don't have a result yet. I don't think we will have a result very soon. But yeah, just trying to show that, yeah, the first algorithm is actually time consuming, especially when the prime number is quite large. And this will happen. We can have even larger prime numbers. Okay. Okay, so let's go back to, yeah, then basically, yeah, it's not, we cannot accept this. Like, we take such a long time. We still don't have a result, how long it takes. I will let it run, and at the same time, I will introduce the second time. So as you see, there's a need, another algorithm should be work much more efficient than this one. Okay, let's go to, let me stop sharing. I will go back, check how many times it will takes. Let me do it again. Okay. Okay, so the second algorithm actually is the same. The only thing is changing here is, yeah, we only need to iterative from 2 to square root of n. Here, if you compare, we need to check here. So basically the only thing changing is here. So here, basically we'll get the square root of n of this number. It may not be an integer, but it is fine. And then basically all the rest should be the same. Okay, then basically this is the second algorithm. But as you see, yeah, we reduce the number of times we need to check. Okay, then yeah, we can also go, yeah, this is algorithm 2. I will also introduce algorithm 3 and do all the experiment at the very last. So algorithm 3 is a different way. Basically, it's trying to do, only need to check 3 things, because for this number, okay, equals to larger than 0, k equal to 1. So for this number, it only include all the numbers like larger than, if you remember, larger than 4. So basically, we also need to check the numbers before 4, whether they are, you know, factors. So we need to check 2 and 3, and then check the rest of those things. So basically, that's why you see here, we need to check whether 2 and 3 is a factor. And then we check here. So basically, the here only thing need to change. So we need to generate a list, basically starting from 6 and 12 and 18. Basically, it's k equal to 1, k equal to 2, k equal to 3. So basically, this is k equal to 1. This is k equal to 2. This is k equal to 3. And we need to make sure that this is smaller. We only need to check till and square root. Okay, so basically that's when we stop. This is the step. As you see, there are the steps between the adjacent number is 6. And this is what we stop. Okay, so basically let's we generate a bunch of numbers. They are all the things here, they are 6k. This is 6 1k, 6 times 1. This is 6 times 2. This is 6 times 3. Okay, and then we need to check whether this number k is smaller, whether we have to compute 6k minus 1 to check whether this is a prime number, which is whether this is a factor. Then it's the code is here. You also need to check 6k plus 1 whether this is a factor, and we check here. Then basically, if any of them is a factor, basically shows that yeah, this is not a prime number. Okay, so basically this is a piece of code. Okay, then let's go and do the experiments. Okay. Let me stop sharing this one and sharing the actual code here. Okay, we got our solution. Yeah, this is a prime number, and the time it takes is 143 seconds. And we find this out. Okay, remember this time. Okay, so this is algorithm 1. Basically, we check everything from 2 to n minus 1. Okay, and here we have another algorithm which is better. We only need to check 2 till n square root. Okay, so let's do this. Let's first checking this one. This is one that Ola shows it's not a prime number. Yeah, it's have the same result. It takes around, it takes no time because it's quite small than one second. And let's check this one. This one is the same. We already checked this one. So basically we need to memorize this. Okay, we can somehow generate mark down here. Okay. So like this. Okay. Yeah, we know that the time we do this, and this time we're using, okay, then we want to compare the same number. They are trying to finding out the same number, whether this is a prime number. Okay, so for the same number, this number, algorithm 1 take 1.6 seconds. And yes, and this one, the same number. This one only takes 0.78. As you see here, we reduced almost only using half of the time in algorithm 2 to show that this is a prime number. Okay, then for 3, I'm assuming this should be around 70 seconds. Okay, we can let it run. So this one, we can let it run. But I guess it will take a while. Yeah, because assuming it should be using half of the time here. Okay. And for the third one, so in Jupyter, we only can run one code. We can open another. Jupyter notebook, and we can, get those things, the third algorithm here, and we don't need to wait. Okay, so first, this is the algorithm 3 we have here. We put the code here. Don't forget that we need to use this module. We need to import thing here. Okay. So basically we can run here. Okay, first we check this one. Check Ola, what Ola proof. Okay, how long it will take? Yeah, approximately the same time because it's only like 600 checkings. What about this one? So for this one, I think the first algorithm takes 1.6 seconds. The second one is around 0.7 seconds. Look at this one. Yeah, as you see here, this one further reduced the computation time as only take 0.3. So yeah, because the number is small, you don't see the time difference. So let's try this this one, the largest one. Yeah, to see how long it takes. I think it still takes some time, but okay, this one is finished. Okay, as I said, it's almost using half the time, as you see here. So this one using 143 seconds to show that this one is a prime number, and this one only using around the 71 seconds to show that. As you already see the difference. Okay, this already done, and this one only using 23 seconds. Okay, although they're doing the same job, but as you see, the computation time, yeah, it's quite different. So basically, yes, the third algorithm is the most efficient algorithm, and the first one is it's not that efficient. The second one is good. Okay. Yes, let's go back to the slides. Okay, so I will share the code with you guys, so you guys can play with this, just changing the number here. Then or you can also try to make this as a function, so you don't need to doing these things again and again. It will be more efficient. But yeah, but the basic idea is we just coding our 2-3 algorithm in Python here, and we can compare the things, especially compare the time they consume. Okay. And any questions? Okay, if not, I think that's pretty much I'm going to cover for Python for loop. Let me see whether I have anything left. I don't have anything left. Yeah, we already did 3 experiments. This one, although quite large, but we show it's not a prime. This one we show it is a prime, and this one we show it is a prime. And we also compare their computation time. Okay, I think that's pretty much for the class. I think there's 10 minutes left. So I don't have many contents to cover, but if you guys want to play with another puzzle, I can show another puzzle to you guys. If not, yeah, I think you guys can leave. Or if you have questions, comments, yeah, you can make.
Yes, thank you so much. I think this is great. Yeah.
Thank you, Chi. Okay, let me stop sharing.